So today we're going to keep talking about um, what we've been talking about, right? What have we been talking about? Antiderivatives. Okay, cool. So in our words, with meaning, right? More accumulation from rate. We are going to apply it to the idea of area by the end of today, but just because we have the time, let's make sure that we understand, what's been going on. So last time I introduced this idea of U substitution as a means for undoing the chain rule. Okay, so the sentence I just said is really important. I don't want you to just see this as a new thing to memorize, right? This is not just a procedure that you can add to your list of rules to memorize about mathematics. That's not what that was, right? What that was an aid to help you organize your thought process in reversing the chain rule, right? Because remember, we learned all of these derivative rules, right, and how they operate, and then when we start talking about an antiderivative, we're literally reversing the process, okay? So U substitution is a tool to help you reverse the process of a chain rule derivative, okay? So let's practice, okay? So I'm going to put a rate of change function up, and I'm going to ask you to simplify this, okay? So take a minute, try to look at the structure of what it is we're looking at and see if you can determine an equivalent expression in closed form for the integral that I've written on the screen. And if you get bored, here's another one. Yeah, so each row is sort of the All right, shall we talk? So let's just make sure that we see the big picture again, right? So what I've done is I've said, hey, this function is the derivative of something, right? I called it a rate of change function. And so when I write this symbol, right, this thing over here with a dx at the end of it, what are we trying to find? The corresponding accumulation from A to B, where the accumulation has this thing as its rate of change function, right? So that's what we're doing, right? Now the nitty-gritty details of it, the way that you can frame your thinking about that is, this is the derivative of some accumulation function. So I'm looking for a function who has this thing as its derivative, okay? So that's what you're trying to do, okay? Now when you look at this, you could eyeball it, right? Or you could use the method of U substitution that we talked about. Now, the reason that I'm saying those things, though, is because the first thing I did when I looked at this, this rate of change function was to look at its structure and say, hey, this is a product, right, of some interesting things. And the only derivative rule that spits out a product is the chain rule. Okay, so what I'm really trying to do is undo the chain rule, which means I'm looking for a composition of functions, right, that will give me this thing as its derivative. So sort of I'm going to eyeball it out loud, okay? So I say, I've got something interesting being squared. That's a composition of functions, right? Now, it would be super convenient if the derivative of the thing that's like tucked inside of another function had its derivative being multiplied, right? Because that's what the chain rule does. Okay. So, well, what's the derivative of 1 plus tan x? Secant squared x. Heck yeah, right? Okay. So that to me is what nominates this thing, the u plus tan x, to be my u. Or sorry, 1 plus tan x is going to be my u. Because if I take its derivative with respect to x, I get secant squared of x, right? And so that means that little changes in u are going to correspond to secant squared x times little changes in x. So if I come over here and I try to rewrite this integral in terms of u, I've got the integral of 3u squared du. Pretty sweet, right? So then notice I'm not messing with the bounds. I'm going to sort of leave them out of my line of sight for the moment and deal with this. So what is a function now in terms of u, right, that has 3u squared as its derivative? U to the third, right? The derivative of u to the third is 3u squared, which means u to the third is an antiderivative of 3u squared. Okay. Now, if we're being super formal about it, we'll write the plus c, right? But remember, we started this problem in terms of x, so let's end it in terms of x, right? So u was 1 plus tan x. So this is really 1 plus tan x to the third plus some constant. Am I done? Why not? I need to evaluate it, right? I was asking for the accumulation from A to B. So that's what my final answer should be. So here's my accumulation function. If I want the total accumulation from A to B, then I do what? Yeah, I look at the total accumulation up to B, and I subtract off the total accumulation up to A. Why didn't I write the plus C's? Because they cancel each other out. They subtract off, okay? So I forgot a cubed right there. So there's that, okay? So if we did it again, let's see. So down here, once again, we're looking at a rate of change function, right? And I'm asking for the total accumulation between 2 and 4. Sorry, -2 and +4 corresponding to this rate of change function, okay? So that means that I'm looking for a closed form antiderivative of this rate of change function. Okay. So my strategy, once again, is to look for the complicated looking thing and see if its derivative is multiplied somewhere else in this expression. Okay. So to me, the complicated looking thing is sine squared of x. So that's where I'm going to start and hope that it works. So I'm going to let u equal sine squared of x, which I'm going to write like this to help me out. So what's the derivative of sine squared of x? 2 sine x cosine x. So that means little changes in u correspond to this much times little changes in x. So if I wanted to rewrite my original integral in terms of u, hopefully it'll look simpler, right? Let's go ahead and do that. So I've got a 2 times u, and then 2 sine x cosine x dx. Hey, That's right there. So that's just du. Okay, super pretty looking, right? So what function in terms of u now has 2u as its derivative? U squared, maybe plus a constant. Okay. So then if I wanted to compute this actual accumulation between -2 and 4, I need to convert back to x's because these are x values. I can't just plug them into here, right? Because this is in terms of u, which we've said is not x, right? This is something different. So let's rewrite our accumulation. So this thing is going to be equal to sine of x squared, but then it's u squared. So we're squaring a square, so it's to the 4th power, right? And we're going to evaluate that from x equals -2 to x equals 4. And so that's exactly what we talked about before, where we're looking at the total accumulation up to 4 and subtracting off the total accumulation up to -2. Okay? Question? Mm-hmm.
If we were just to find the antiderivative and we left it sine squared x all squared instead of combining the x.
Oh, that's fine.
That's fine.
Yeah. Mm-hmm. Not a problem, because they're equivalent, right? It's the same thing. This was not the only way to do this second problem. You could have, for example, multiplied the 2's together, multiplied the sine squared times sine, and then done a u substitution where your u was just sine of x. That also would have worked. Okay, so that's another thing to keep in mind, is there's not necessarily just one way to do it. Just because this is the way I showed you doesn't mean that's the only way. Okay, this is where you get to be a little creative and have a little fun with it. Okay, so so that's the technique that we practiced on Wednesday. Let's see what else, right? Because like I said, I don't want you to lose track of the fact that we're actually doing meaningful things, right? We're not just learning procedures. So let's check for understanding really quick. This originally said quiz, but I promised somebody the other day that I wouldn't do any in-class quizzes. So, so check for understanding, okay? Treat this as if it were a quiz, okay? So what does this thing mean, and what would it equal? How many people are trying to find an antiderivative right now? How hard is that? It's really hard, right? Take a moment, think about what do the symbols on the board mean. Take a minute, talk to your neighbor, and break down what every don't try to just do something, right? This is the thing that I'm trying to get you away from. Don't look at a problem and say, what am I going to do? Ask yourself, what do these things mean? Okay? So break apart all of the components piece by piece. Start on the inside and work your way out. What does the sine of 3 cosine x mean? And then what does the integral from 4 to 7 of sine of 3 cosine x dx mean? And then what does it mean to throw that d over dx symbol out in front of that? Okay, break it all down. Talk to your neighbor. Just in case you've already figured it out, I'm going to put another one. Oh, maybe I'm not. Oh, it's going to give you the answer if I press it again. Are you ready for it?
Yeah.
I'm so excited. Wait, before I show you the answer, let's break it down. So what's the thing on the inside represent? Okay, so I heard rate of change. Is that a function or a value? It's a function, right? So the sine of 3 cosine x is a rate of change function. We're going to get as precise as we can these days, you guys, okay? And then when we add in this integral symbol from 4 to 7 and tag on the dx at the end, what does that mean? It's the value of what? Can I get one person who's brave? Rochelle.
That is the value or the accumulation between 4 and 7 of a function with that rate of change.
Beautifully said. Beautifully said. Okay, so then I'm going to throw in this mysterious symbol ddx in front. What does that mean? It's asking for the rate of change of the thing inside, like next to it, right? But what did we just say the thing next to it was? A value. It's a constant. So what's the rate of change of a constant? 0. What? Okay. So then, let's do it again.
No.
Yeah.
Seriously, all of them.
Now, see what you can do with this. You think it's going to be 0? No. Gotta think. Gotta work. Because let me tell you, you can't. I have not given you the tools to find that antiderivative in closed form. So don't try.
What we just did, you had the right answer. What we just did is y is the answer. And you can be given different problems where you have to do this. You can't just change that thing for an x. So there's other examples where you need this process. You need to know that process in order to get a harder one right. You can't just say, oh, it's just the rate with x instead of p. So watch out. For this one, that worked. But practice that process. Did that make sense?
I'm so jazzed, you guys. Such good thinking is happening. Okay, so I've heard some super cool explanations. In the back, we had a good one. You want to share it with the class? Okay. Yep. So, right, if we think about what the meanings, so this is a rate of change function. And then looking at the next layer, this is the accumulation from 4 to x, right, where this is the rate of change of that accumulation function. And then we're asking to find the rate of change of that. Okay? So I'm going to make it a little bit more precise, but that's sort of the idea. So I wanted to make sure that got out there. So, so what does that give us as the final answer? It was, you said it. It was, so sine of 3 cosine x. Okay, so that would be fairly convincing to your neighbor. Maybe a little less convincing to a mathematician because we're picky about the way we take explanations. So let's sort of firm it up a little bit, okay? So we just said that this is a rate of change, is the rate of change function for some accumulation function. We already decided that it was beyond the scope of our desire and abilities to try to find that accumulation function in closed form, but I know it's out there, right? There's some accumulation function who has this thing as its derivative. What do you want to call it? Oh, no. G of x? I like it, g of x. Okay, so we're going to call an antiderivative of this thing g of x. Okay, so g prime of x is sine of 3 cosine x. Okay, which means g is an antiderivative of this thing, right? That's the meaning of antiderivative. Okay, so then when I look at the integral from 4 to x of this rate of change function, I'm going to copy this down because that's still what we're trying to do. But just looking at this part of it now, this is the accumulation from 4 to x with this rate of change. So I would write that as what? G of x, right, minus g of 4. So I'm trying to take the derivative now. Let me split this up. So I'm taking the derivative now, finding the rate of change of g, and then subtracting the rate of change of g of 4, right? Because when you take the derivative of a sum or a difference, you take the derivative of the pieces and still add or subtract them. Okay. So what's the derivative of g? G prime x, right? Which was this thing. So this is equal to sine of 3 cosine x. And what's the derivative of g of 4? Why is it 0? Yeah, g of 4 is a value, right? It's a constant. Okay? So it's just the derivative of it is 0. Ha! Super cool, right? So we've really firmly and concretely explained why our intuition worked, right? This is good. This is so good. Okay. So there it is written out a different way. Okay. What time is it? Oh, shoot. I promised you I'd talk about area today. I got so excited about this stuff. Should we talk about area? No? This is helpful? Oh, okay. Yeah, the area is on the homework. Yeah, so we should talk about it. Okay. I'm going to throw this one up here, and we're going to talk through it, hopefully quickly, because we just did something a lot like it. Notice I've got the derivative of an integral all over again, but instead of going from 4 to x, I'm going from 3 to 4x to the 5th. Ooh, so that gets a little bit more interesting. Now let's, so if we apply the same theory that we just did, right? And we said like maybe big F is an antiderivative. That should be a V of 7e to the 2t, right? Then, or I guess I'll use an x for that. Then we're trying to find the derivative of what? F of 4x to the 5th minus f of 3, okay? And so now when I take the derivative of the pieces, I'm not just looking for the derivative of f of x, right? That would be easy. Instead, I'm looking for the derivative of f of 4x to the 5th. What does that remind you of? What we just did, but it's a little more complicated, right? Because this is not just an x. Oh, it's a chain rule. It's the theme of the day. Okay, so we got the chain rule, right? So when I take the derivative of this thing, yes, I have to apply the chain rule. So it's going to be f prime of 4x to the 5th times 20x to the 4th minus 0, right? And then remember that we did know, right? So f was an antiderivative of this function. So f prime is this function, right? So this will be 7e to the 2, but instead of an x, I'm keeping in this thing, 4x to the 5th times 20x to the 4th. Okay? So I don't want you to fall into a habit of just, so this is why we make it precise, right? This is why we actually take the time to write out, oh, here's an antiderivative, because it's so easy to fall into the mindset of, oh, well, I'm taking the derivative of an accumulation, so it's just the rate where I plug in x. It's not quite that simple, right? Because we can look at accumulation where we're accumulating to interesting things, okay? And so it adds a layer of complexity. Okay, so that was my word of warning. Oh, so many good things I had for you. Okay, and then this was going to be to make sure that you're still thinking in terms of everything that we've done. We can come back to that on Monday, maybe. Okay, so let's talk area real quick. Okay, so we built up accumulation from rate of change by building a step constant rate of change function and saying, hey, I can get little bits of accumulation by taking a constant rate and multiplying by a little change in x, right? And that gives us little bits of accumulation. And so then by the time we get to a certain x value, we've added up all the little bits of accumulation to give us our total accumulation at that x value, okay? Now, some people have taken this idea and said, well, if I look over here on the left, the rate in the first chunk times a delta x gives me the area of that chunk. And again, and again. And so if you really want to make a stretch, right, you can say, well, then integration, right, looking for accumulation, is just looking for the area under a curve where the curve is a rate of change function. Okay, so this is a really commonly taught idea in calculus. Unfortunately, it's usually perceived as the only meaning for integration, which is why I'm not giving it much time here, because it is not the only meaning, right? We've talked about so many other cool ways of interpreting it as accumulation and not as area, okay? But it does exist. Did this little, I feel like this little diagram was pretty, like, clear. But does anybody want me to say it again? Yeah. So when we look at our interpretation of taking constant rates, gives us little bits of accumulation by doing those constant rates times delta x's. Well, I could sort of pretend that I wasn't thinking over there and instead just concentrate over here and say, okay, well, if I take this rate and I multiply it by a little change in x, that's exactly how you would compute the area of this rectangle under this blue line, right? And then the area of the second rectangle, and the area of the third rectangle, and the area of this rectangle. So you could interpret the meaning of doing an integral, right? So if I were taking the integral from 1 to some x value, that we talk about that as accumulation. And we think about it as doing these rates times little bits of changes in x to build up accumulation. Well, what you could do is say, well, if I take this idea and still focus on this picture, then the numbers I'm getting over there correspond to adding up areas under this curve. Okay? So that's the idea. So if you want to find area under a curve, you can do that by using the integral. Okay? So so one more time, the pretty picture. Okay? And then, of course, if you let delta x get small, then the areas get closer to the actual area, right? Until it's essentially just, so that accumulation value on the right graph, right, is represented by this vertical line segment, right? That value is the area under this curve, right? Because we got that value by adding up rates of change times little changes in x, which is exactly the areas of little rectangles over here. Okay? So far, so good? Okay. So this is a way to interpret integrals. I'm sort of bashing it. I'm sorry. I shouldn't bash it. It is a legitimate application of the integral. Okay. I really just don't want you to think that this is the only thing. So hopefully me telling you this isn't going to make you forget everything else. So the most common time that you'll see this is when you're asked to find areas bounded by curves. Okay. So if I wanted to find the net area bounded by the graph of G, the x-axis, and two vertical lines, x equals -1/2 and x equals 4, that's going to look like this, right? So I've got x equals -5, x equals +4 are the vertical lines. The x-axis is another bound, and then the curve itself is the other bound, okay? And so that captures 3 different areas, okay? And so why on earth did I say the net area? So in the blue, right? So remember, we're interpreting the curve itself as a rate of change curve, okay? And so down here, the rates are negative. So you're multiplying a negative number times a little change in x. That's giving you a negative area. Okay, so this is why I say it's a superficial meaning, because negative area is nonsensical. Okay, but that's the way we're going to interpret it, right? So we've got positive area, because the corresponding accumulations here are positive. And then down here, though, we're getting negative bits of accumulation. Okay, so it corresponds to a negative area. So if I just were to take the integral from -1/2 to 4, right, that's going to give me probably a negative number, because this area is so big and it's negative, right? The total output is going to be a little bit positive plus a lot negative plus a little bit positive. I'm going to end up with a negative answer, okay, if I were to actually compute this integral, okay? But oftentimes, rather than trying to find the net area, you're asked to find the total area, okay? In which case, you should know what, so in which case you actually have to make sense, okay? So we're not going to allow for talking about negative areas if you're asked to find a total area, okay? You want to legitimately talk about the concept of area the way that we usually talk about the concept of area. So you want everything to be positive, okay? Well, if I still have this picture where I've got positive, negative, positive areas, that's not going to work, right? So instead, I'm going to have to break it up into chunks. And I'm going to say, okay, well, I can find the area the way that I think of area from -1/2 until this point in the normal fashion by taking the integral from -1/2 until this x value. Okay. But then here, if I were to just take the integral from here to here like I normally do, I'm going to get a negative output, right? A negative value will come out of that integral. So how do I make a negative into a positive? Either take the outside value or just multiply it by -1. Okay? So if I multiply the integral from this x value to this x value of g of x by -1, that'll now give me a positive value that I can interpret as the area of this blue region. Okay? And then I'll add from this x value, the integral from this x value to 4 of g of x to get the area under the red. Okay? So in order to do that, you have to figure out x-intercepts, right? So you have to determine where does the graph cross the x-axis so that you can split up the region into positive areas and negative areas, and then account for the negative area with a negative, okay? So then when I find the total area, I'm going to add up those values, and that will give me the total area, okay? So that will get you through your weekend homework assignment. You do have a quiz next week, and I've posted the information about it. And then I've got plans, some review materials for Monday, maybe a game for Wednesday, and then opportunities for asking lots of questions next week, okay?